pandas series and data frame. So first, we look at list. So we create a list with about 20 elements. Then, for calculating the mean of a list, so we have to define a function here. In the function, it's just the sum of this list and divided by the length of this list. Then we can call this function to this list. So the mean has been calculated. To calculate the median of a list, first we have to sort this list using sort function. Then we calculate the mid index of this list using integer division. Then we have to plus 2 elements in the mid of this list, then divided by 2. So no matter the length of this list is odd or even, so the number will be the median of this list. So the list has a median 6.5 here. And to calculate the mode of a list, we have to import the function called mode from package statistics. Then we just use the mode function to this list. So the mode of this list is 8. So next we show how to calculate these 3 measures for NumPy and the array. So first we import NumPy and create and end the array of 500 elements. Then we just use NumPy's min function to this array. So the mean is about 52.64. Then we can also use the NumPy's median function to this ND array. So the median is 52. And to calculate the mode of NumPy array, we can import the function called status from SciPy module. Then we can use this status module submodules function called mode to this ND array. So the mode of this array is 27 and its count is 15. And for pandas series, we first import pandas and create a series. So the series has 5 elements with the index A, B, C, D, E. Then we can just use this series min function. So s.min can get the mean value of 6.6 of this series. Similarly, we can also use s.median to get the median of this series is 9. And we can also calculate the mode, just use s.mode. So the mode of this series is also 9. And for pandas data frame, first create data frame. There are 4 columns A, B, C, D, and 5 rows with the index 0 to 4. All the elements are numeric. So we first calculate the mean of each column of this data frame. So we have to use dataframe.min function. Then inside the option, we have to specify axis equals 0. So the result is a series data structure with index A, B, C, D for each column of the column of this data frame. Then the value is the mean value for each column. And if we want to calculate the mean of each row, we just assign axis equals 1 here in the mean function. So the mean value for each row index 0 to 4, has been calculated. And we can also calculate the mean of a specific column of this data frame. So we just use bracket quotes A for the column A of this data frame, then use the function .mean. So the mean value of column A is 13.4. And if we want to calculate a specific row of this data frame, we can use data frame.log, for example, the second row. So we put the 1 in bracket, which means the second row of this data frame. Then .mean can get the mean value of this row. So the mean value of second row of this data frame is 6.25. So for the median function, also we have the same mechanism, just assign 0 if we want to calculate all columns median of this data frame, or we just want to calculate each row median of this data frame. So this is the median of each column. And this is the median of each row. And for the specific column, the median, it's also quite similar as the mean. We just select the column and then use .median. So the median value for column A is 5. And if you want to calculate the median value for the second row, for example, we can use data frame.log 1 in the bracket, then median. So the median of the second row is 3.5. So for the mode, also quite similar as mean and median. So for the whole data frame, if you want to calculate the mode for each column, you can just use data frame.mode, then axis equals 0. So the mode for each column has been printed out. And mode for each row, we just put the axis equals 1 here. So here we have seen for the first row, just show the original number. Why? Because each number occurs one time. So pandas cannot calculate the mode for this row. But for the second row, there's a mode for the number is 2. So other elements is not a number here. So for the rows mode, only second row has a mode. Other rows has not mode. So the original numbers show for other rows. And for the specific column, for example, column A dot mode, we can get the mode of this column. So column A's mode is 5. And for the second row of this data frame, we can also calculate the mode. So the second row's mode is number 2. So number 2 occurs 2 times. In this video, we will introduce binomial distribution and show how to draw binomial random numbers in Python. binomial distribution is a probability distribution that summarizes the likelihood that a variable will take one of two independent values under a given set of parameters. And the distribution is obtained by performing a number of so-called Bernoulli trials. An experiment can be called a Bernoulli process if it has the following properties. First, the experiment consists of repeated trials. And second, each trial results in an outcome that may be classified as a success or a failure. So the result of a Bernoulli process is binary, yes or no, success or failure. And the probability of success, denoted by P, remains constant from trial to trial. And the repeated trials are independent. So which means each trial has no effect on the result of other trials in the total n trials. And the number x of successes in n Bernoulli trials is called a binomial random variable. And the probability distribution of this discrete random variable is called the binomial distribution. And its values will be denoted by b, x denotes this random number, n, p. N is total trials, p is probability of success in each trial. So for example, flipping a coin repeatedly is an example of a Bernoulli process. And the number of heads occurring among n times flipping follows a binomial distribution. So the formula to calculate the probability of random variable x, which means how many times of success will occur during the process of n trials, with the probability of p for the success for each trial, is a combination of nx times p x quotes and q n minus x quotes, and q equals 1 minus p. So x can be 0, 1, 2, 3 to n. And the mean and variance of the binomial distribution b, x, and p, mean equals n times p, and variance sigma square equals n times p times q. So we will show how to work with binomial distribution in Poisson. In Poisson, the SciPy stats module contains various functions for statistical calculations and tests. And the stats function of the SciPy stats binom module can be used to calculate a binomial distribution using the values of n and p. So the syntax for this function is scipy.stats.binom.stats with np for the parameter. And it will return a tuple containing the mean and the variance of the distribution in that order. So next example is calculating a distribution table. So we define n and p and define a list of values of r from 0 to n. Then we get the mean and the variance of this distribution. And for each r, we calculate the PMF and store in a list. PMF is the probability of binomial distribution for this random number. So we have to import binom from this module. Then we set n equals 10, p 0.2 for each trials success rate and the total trials is 10. So next, we define a list of integer number from 0 to n. Because success can occur 0 times, can occur 1 times, can occur 2 times, and so on, and at most occur n times of all n trials. So next we use the binomial module's stats function to calculate the mean and the variance of this distribution. So the mean is 2, and the variance is 1.6. So this is actually the result of n times p. These two numbers multiplication will get 2 for the mean value, and n times p and times 0.8 equals 1.6 for the variance. And the SciPy binom.pmf function is used to obtain the probability mass function for a certain value of r and p. So we can obtain the distribution by passing all possible values of r possible from 0 to n. So the syntax for this function is scipy.stats.binom.pmf, and with r and p the parameters. So can calculate binom PMF for each value of r, calculate this probability, and put in a list. So if we show this list contains 10 numbers representing the probability of, for example, 0 times occur during 10 times trials is about 0.10. And 1 times occur success of all 10 times trials is about 0.26. And so on. The next we just print its values, print it out, and print mean and variance. Mean is 2, variance is about 1.6. So next example is showing plotting the graph using matplotlib, pyplot bar chart for a number of binomial random variables. So first we import binom and plot matplotlib pyplot function module. So this time we set large number with n equals 1000 trials, and the probability is same as before, 0.2 for success rate for each trial. And we define a list of integer from 0 to n. Next we calculate the probability for each random variable in this list, then put in a list same as before. So this list includes 1000 items. So next we present in a bar chart of these 1000 probabilities associated with this random value. So it is clear that almost like a normal distribution with symmetric along for each side of the mean is about 200. Thanks for watching. Hello. In this video, we will show how to calculate variance and standard deviation using Poisson. So we know sample variance comes from this formula. So this is all the observations, and this is the mean value or average value of the sample. Then we take the difference of these two and take a square, then sum together, then divided by n-1. We divide n-1 here because in the sample variance, 1 degrees of freedom is lost by calculating the mean value. Then for the sample variance s square, we take a square root, then we'll get standard deviation. So next we will show how to calculate these two in Poisson. First, we load the module NumPy. The NumPy is the most common library in Poisson for calculating. Then we create an array, random number with a normal distribution with mean 50 and a standard deviation 10 with 20,000 observation for this NumPy array. We show this array, one dimension, no array. We show first 10 number. They come from normal distribution with mean 50 and a standard deviation 10. Next, we can use std function times from NumPy to just salary.std and with parentheses. So this is 10, about 10. And we can also use salary.var to calculate the variance. You can see the variance 100 about the square root of 10. In this video, we will show how to implement Poisson distribution in Poisson. So first, we will talk a little bit about Poisson distribution. Poisson distribution is used to model the discrete count event occurrence in a specific period. This can be a time period or the area, specific area, for example. And the number x of outcomes occurring during a Poisson experiment is called a Poisson random variable. And its probability distribution is called the Poisson distribution. So the mean number of outcomes is computed from mu equals lambda t. So the t is specific time, distance, area, or volume of interest. And the lambda is called the rate of occurrence of outcomes in a unit time period, a unit distance, unit area. And the calculation of the probability for specific occurrence of number x in this time period, for example, 3 hours, so can be calculated as the division of two parts. The denominator is this number's factorial. So for example, if we want to find out the probability of occurring 2 times in 10 hours. So here we have to fill in 2 factorial in denominator. And in the numerator part, the 2 parts multiplication. The first is power. The power part is negative lambda t. So lambda t is also this mu. For example, we know average 1 point time occurrence in 1 hour. So 10 hour lambda t will be 15 here. So the next part is also 15th. Power is 2 here. So this formula is called the probability of Poisson random number with p x lambda t. So usually we often use mu here, just mu. So mu represents the average occurrence in the long run, the average occurrence in this time period, not necessarily the unit time period. It's any time period in this for this mu. So the Poisson distributions mean and variance are equal. They are both equal to mu equals lambda t. So we only has one parameter is enough to define a Poisson distribution, and this parameter is mu. So the average numbers occurrence in the long run or lambda t for this time period. So in Python, mainly we use three functions to work with Poisson distribution. The first is Poisson.RVS. It uses to generate random number, and this random number is discrete, maybe 1, 2, 3, 4, and so on. Depends on the mean average occurrence in this period, right? And second function is Poisson.PMF. This is a probability function used to calculate the probability of this random number or occurrence time in this time period. And the third is CDF, cumulative distribution function. So this is used to calculate the cumulative probability up to this discrete number. So for example, we want to know the probability of occurring 0, 1, 2, 3, 4. 1, 2, 3, 4 is the total probability of these 4 occurrence during a specific time period. So next we will show some examples to perform Poisson distribution in Python. So first we have to import a Poisson module from package scipy.stats. So scipy is a statistic package. If we have to check if it is not available, so we have to install scipy. But usually this is bundled with Python installation. If you use Python in, for example, framework of Anaconda. So next we generate random number from Poisson distribution with mean 8 here. And we sample 20 random number. So we'll see how it is going. So the 20 random number will be returned as an array, and the array, and you can see 4, 7, 5, 8, they're all discrete number around the mean 8. So next is used to calculate the probability related to the specific count value from Poisson distribution. So we also load Poisson module, then calculate the probability of occurring. So this example is, for example, a store sells 8 ice creams per day on average. So what is the probability that they will sell 10 apples on 10 ice creams? So what is the probability that they will sell 10 ice creams on a given day? So this question is, we want to know the probability associated with a particular count number. So here this count number is 10. And we know the average or the mu or the lambda t is 8 here in this time period. So we just use Poisson.PMF k equals 10 and mu equals 8. So very easy. This is about 0.1. Only 10% you can get exactly. This is exactly 10 occurrence in this given day. So next function is Poisson CDF. We will apply. The example is to calculate the probability that's less than some value, this discrete value. The example is a call center has an average of 5 calls coming in per hour. And what is the probability that this call center has 4 or less incoming call during a given hour? So here, the given hour is the unit time. Also, this is a specific time we want to focus on. So this 5 is the mu, also lambda, because 1 hour, so 5 times 1 is also 5. So we can specify this 5 as the mu of this given hour, right? And what we want to know is the probability, cumulative probability of occurring 0, 1, 2, 3, 4 in this given hour. So load the module. Then we calculate Poisson.CDF. Here's cumulative distribution function with k equals 4, mu equals 5. About 0.44. So about 44% of the time will have incoming call less than or equal to 4. And the third example is to calculate probability which is greater than some value for the counting value. Where occurrence is greater than some value. So certain store sells 15 cans of tuna per day on average. And what is the probability that this store sells more than 20 cans of tuna in a given day? So here we want to know the probability of Poisson distribution with this count number which is larger than a certain value. So we can calculate the cumulative probability of less than or equal to this certain value. Then use 1 minus this cumulative probability. Right? So we just fill in k is 20 and mu equals 15. So that's about 0.0829 of the probability that this store will sell more than 20 cans in a given day. So quite infrequent occurrence of this event, right? It's a very low probability to sell more than 20 if average is 15 in a Poisson distribution. So in summary, we can use 3 functions in Poisson distribution in Python. So RV is for the random number generation and a PMF for the probability function for a specific count number. And the CDF is a cumulative distribution. No matter we want to calculate less than some value or larger than some value. So thanks for watching. In this video, we will introduce normal distribution and show how to use normal distributions in Python programming. The normal distribution is most widely used distribution in statistics. And a continuous random variable x if have the bell-shaped distribution, so it can be called a normal random variable. And the mathematical equation for the probability distribution of the normal variable depends on the 2 parameters, mu and sigma, which is the mean and standard deviation of the distribution. And the density function of the normal random variable with mean, mu, and variance sigma square can be calculated as n x. X represents the normal random variable, and with the 2 parameter mu sigma, density function is a factor in the denominator is square root of 2 pi times sigma. Then 1 divided by this term, then times is power function. So in the power part, it's minus 1 divided by 2 sigma square, then times x minus mu, take square. So the possible value for normal distribution can be from negative infinite to the positive infinite. And the normal curve, this is the density curve, and you can see about 68% of observations or data lies in 1 sigma around the mean. So this is the mean. So this curve is the standard normal distribution with mean equals 0 and sigma equals 1. And about 95% of data lies in 2 sigma around the mean. And about 99% of points lies in 3 sigma around the mean. And one of the reasons why normal distribution is so widely used in statistics is that the central limit theorem states that if we take the mean of a large number of data points collected from independent and identical distributed random variables, then the mean of this data will follow a normal distribution regardless of the original distribution. So which means we do not need to know which kind of distribution comes from of these data points. But if in a large number of data points collected from the same independent identical distribution, then the mean of their values follow a normal distribution. And the areas under the normal curve. So the curve of any continuous probability distribution or density function is constructed so that the area under the curve bounded by the two ordinates x1 and x2 will be equal to the probability that the random variable assumes a value between x1 and x2. So from this density curve, this is the density curve for the continuous random variable. This shaded area represents the probability of the possible value of x between the value x1 and x2. So this shaded area represents the probability. And its probability is px between x1 and x2 can be calculated as the density function, normal density function, take integration with the lower bound x1 and upper bound x2. So if we fill in this form with the normal density function, so the calculation can be done with this form. And in reality, if we want to calculate the probability of normal distribution, usually we have to first transform the normal random variable into z value. The z value equals the x value minus the mean, then divided by its sigma. So z value is called standardized value of normal distribution, or z value follow a normal distribution with mean equals 0 and a standard deviation equals 1. So it's called standard normal distribution. And there's a table called standard normal distribution probability table. So this table lists all values, possible values for cumulative probability. So this is density curve. Density curve for the standard normal distribution. So this density curve around the mean equals 0, and any value shaded area up to any value means the probability of this random variable between negative infinite to the z value. So also we say if we want to know the probability of x less than this z value, we just take this area, shaded area, we can get this probability. So this table actually lists the probability of this shaded area. So if we want to know, for example, the probability of x less than 0.88, so we just check the line of 0.8 and find the column of 0.08. So plus this 2 is 0.88. So find the value is about 0.81. So which means about 0.81% of the values in this normal distribution less than the value of 0.88. So this here the say value is 0.88 and the shaded area is about 0.81. So next we will show some examples of using normal distributions in Python programming. So we go to Python Spider from Anaconda, and first example is shoot histogram plotting normal distribution. So we have to load the NumPy module and matplotlib module to plot. Then we define the mean and the standard deviation of this normal distribution first. And we want to draw the random number from this normal distribution. So we will draw 3,200 random numbers that follow this normal distribution, right? So we define the size equals 3,200. So next we will use the function called NP. This function from NumPy's module. So NumPy's random module has a normal function. So numpy.random.normal. This function will create normal variables, create random numbers following this normal distribution. With this mean, this is standard deviation, how many such numbers we want to draw. So we run this statement. So values have been created. Next we will plot this value in a histogram using matplotlib's plot function. Plot.histogram hist function. This value and with the bin, how many bin. And we add a vertical line to denote the mean value in the figure. So these are random number actually. These are not perfectly matched to the normal. You can see here a little different, and this shape not perfectly symmetrical, but it's a shape quite close to the normal, right? Because it's a random number generated. So each time the random number generated may not be the same. I can see the mean about 32 here. So next we will use a student score example to show several functions using normal distribution. So the problem is, suppose the students test the scores follow normal probability distribution, and with about the mean equals 81 and standard deviation 18. So first question is calculate the percentage of students who have scores less than 60. So the solution is we can use SciPy. SciPy module starts norm function. So we will show first we load SciPy's norm and NumPy. And we define some factors of this normal distribution. So mean is 81, standard deviation 18, and the students have 100 students. And the scores, we want to know the percent of students has scores lower than 60. So we set scores is 60 here. So we have said most of calculation of the normal will be connected with the standard normal distribution. So first we calculate the z-score, which transform this number score as a standardized value. So this means z-score. Z-score is for the standard normal distribution. So the score number minus mean and divided by its standard deviation. So for example, we can show this score value about negative 1.16. Then we calculate the cumulative probability in a standard normal distribution using norm.cdf function to this z-score. If we look at this shape, so we want to calculate the probability of this shaded area to this z-score. We have calculated this z-score. So just run this statement. Can show about 0.12. So next we calculate this as a percent value. So about 12.17% of the students have scores less than 60 in this example. So the second questions associated with this example is calculate the percentage of students who have scored more than 90. So it's quite simple to get the percentage of people who have scored more than 90. Okay, here is 95. We use 95, change 95. More than 95, we first find the probability of people who have scores less than 95 because the cumulative function is used to calculate the probability less than some number. So we first have to find the probability of scores less than 95. Then we will subtract the probability from 1. So we use 1 to subtract this cumulative probability. Then we will get the probability of people who have scored more than 95, right? So it's quite simple. This is same as before. We just set the score as 95 here. And the same as the previous example, we calculate the probability and the z-score and the probability, cumulative probability of this z-score. Then we use 1 minus this probability and times 100. Then we'll get a student's percentage who get more than 95 score. So there are about 21% of the students get more than 95 in score. And third question is calculate the percentage of students who have scored more than 75 and less than 85. So if you want to calculate, for example, more than 75, less than 85. So this means we want to calculate the shaded area of this shaded area. So we first have to calculate the cumulative from negative infinity to x2. Then we calculate of this area. So cumulative probability from negative infinity to x1. Then we use the first result minus the second, we'll get the shaded area. So for this question, we define two, say the score 75 and 85 first. Then, similar as previous examples, we first transform these two scores to the z value, so-called z minimum score, the maximum score. Then use the norm CDF function, we'll calculate the cumulative probability associated with these two scores. So next, we just calculate the division between these two, then times 100 to get the percent value. So there are about 21% of the students have scores between 75 and 85. So the last question of these examples is try to find the score under which there are about 80% of the students' scores. So this question is, we want to calculate the z-value here now. So in this question, we know the area, we know how many percent of the students here, but we want to find the z-value. So this actually is the opposite operation of the previous example, right? So here we want to find the point at which there are about 80% of the students under this point. So we first also import module and define the mean value, student standard deviation. Then here we set a Q score. So Q is the probability. We set Q score here 0.8 first. So next we will use a function called norm.ppf. So ppf is the inverse function of the CDF in norm module. So ppf will find the z-value. Find the z-value, if we just put in a Q score here, we find the z-value for standard normal distribution associated with this cumulative probability. So Q score is the probability, right? So calculate with this statement. Then next we have 2, because z8 is the z-value for the standard normal distribution. So we have to transform back to the normal distribution with this mean and this standard deviation. So we have to use this one, result of this z-score times standard deviation, then plus mean. Then we show this z-score. About 96. So there are about 80% of the students have the scores lower than 96 score. Great, right? So an alternative way is that we can just use the norm ppf with this Q score 80%, 0.8 here, and we set an option called the log, just input this mean, and scale, just input this standard deviation. So use this option, so we do not need to transform back because this directly transform back with the z-scores associated with this normal distribution. Run this and we show the value. It is saying that about 80% of the students had the scores lower than 96. Thanks for watching. This video will show how to conduct Shapiro-Wilk test for normality in Poisson. So many of the statistical procedures are parametric tests based on the normal distribution. For example, the rationale behind hypothesis testing relies on having something that is normally distributed. So it's very important that you have to check the normal distribution assumption of the data before deciding which statistical test is appropriate. So the Shapiro-Wilk test or Shapiro test is a normality test in frequentist statistics, and the null hypothesis of Shapiro test is that we assume the population is distributed normally. So if the value of p from the test is equal to or less than, for example, 0.05, then the hypothesis of normality will be rejected by the Shapiro test. And in Poisson, we use Shapiro function for normality test. So next we show 2 examples in Poisson. So first we load import several module for NumPy, and from scipy.stats model import Shapiro, and from NumPy's random model import random n. So we create an array of 1000 number from normally distribute random number generate. So test data now includes 1000 numbers. So next we use Shapiro test of this test array. So you can see from the results, listed statistic is about 0.99 and the p-value is 0.42. So since this p-value is much larger than 0.05, so we does not reject the normality hypothesis. So we does not reject the null hypothesis here, which means we have not evidence that we can reject the normality hypothesis of the data. Example 2, we also import several modules, NumPy and Poisson, which we will generate data from Poisson distribution, and the seed module to create a seed, and the Shapiro and RDN. So this time we create test data of array from Poisson distribution with mean 5 to 100 random number. So test data include 200 discrete random number from Poisson distribution. As Poisson distribution is not normal and is a discrete random number generated. So let's run the Shapiro test data for normality tests. So this time the test statistic is about 0.96 and the p-value is 0.000119. So it's much lower than the p-value of 0.05. So we have strong evidence to reject the normality hypothesis from this Shapiro test. Or we can say these data observations are not normally distributed. Thanks for watching. We will talk about exponential distribution and show how to use exponential distribution in Python. The exponential distribution is the probability distribution modeling the time until next Poisson event comes. So exponential distribution's variable is a random variable, larger than 0. And it is a particular case of the gamma distribution when alpha in gamma distribution equals 1. So this is the exponential distribution's density function. So there are a parameter called beta. Beta is average time or mean time in the long run, the average time between the two events in a Poisson process. So the function is 1 divided by beta times e minus x divided by beta's power. So sometimes we also call 1 divided by beta or the reciprocal of the beta called lambda. So this is called the hazard rate in Poisson distribution. So the reciprocal of the beta lambda is the mean event rate in a given time unit. So beta is larger than 0. And the mean and the variance of the exponential distribution, so mean equals beta and variance equals beta squared. So next we will show several functions used in Python to model or calculate exponential distribution. So we have to import a module called Expon from scipy.status and numpy and matplotlib, these three modules. So the first function we will use called RVS from Expon module. So RVS will generate random number from exponential distribution. So beta is also called scale. So this means the average time between two events in exponential distribution or in Poisson distribution. So we just use expon.rvs random number, RVS scale equals 2, size 10. We want to generate 10 such exponential random number. And this, so we'll print. So these 10 numbers are random number generated from this exponential distribution. You can see this range from 0.44 around 2 to 5. The largest number about 5.78. Because we have beta equals 2, the mean number is 2. So it's quite reasonable around 2, right? So next we will create probability density from value of the exponential random number. So we create a series NP arrange, create about 300 values between 0.01 to 3 with the gap 0.1. So this numpy array will represent the exponential random number. And this number is about 30 values, so not 330 values. And next we will use the function called PDF in the Expon module. So probability density function. Then calculate the density functions of this array. And we use scale 1, which means beta equals 1 now. So this means average time between two events is 1. Just to learn this function, and we plot the density function of these 30 values. So this is exponential density function with beta equals 1. So the third function we will show is called CDF. So this is a cumulative probability density. We will also create a quantile array first, this time about 90 values. Between 0.01 to 9 with the gap 0.1. So we can next run this function expon.cdf cumulative probability function of this array, also with the scale 1. Then we plot the curve between quantile and this cumulative probability. So you can see quantile is a non-decreasing curve from 0 to 1, represents the cumulative probability. You You see, the beginning increase very fast because in the last run we see the density is like this shape from 1 to 0. So density in the beginning is very high, about 1. So the beginning, the cumulative increase very quick. Then it becomes slower, becomes the density become less and less and close to 0, right? So this is the cumulative probability function for exponential distribution with beta equals 1. So in sum, for the exponential distribution, we can use 3 functions. For the XPON modules, RVS function can generate a random number. We have to set a beta called scale, and with the size how many random number we want to generate. And if we want to show the density function, we can use exponential.pdf function. And input, of course, we have to set the beta function, which means the mean time between 2 events. And the quantile is an array of the value we want to generate from. And the third function called CDF will generate a cumulative probability function with the input same as PDF, with beta value and an array for exponential random variable. So this variable is positive number. So cumulative probability generated is from 0 to 1. We will show how to conduct chi-square test in Poisson. We will first briefly introduce chi-square distribution. So chi-square distribution is a continuous distribution with degrees of freedom. So it is used to describe the distribution of a sum of squared random variables. That's why the name in the distribution has a square. So chi-square distribution's random variable is called second moment random variable. So it is also used to test the goodness of fit of a distribution of data. So this is in a linear regression, and whether data series are independent. So this is called independence test, and for estimating confidence surrounding variance and standard deviation for random variable from a normal distribution. And if say 1, say 2, say n, an independent standard normal distribution random variable, then x, if x is the summation of say 1 square, say 2 square, and plus should say n square. So x will follow a chi-square distribution with n degrees of freedom. So the notation of chi-square distribution is chi-square n. So this figure shows several chi-square random variables density curve with different degrees of freedom. So for K1, this line. Now for the K2, this line. So for the K2, actually, it is an exponential distribution. So in application in regression, S is R, which means sum of squared residues divided by sigma square, has a chi-square distribution with n minus 2 degrees of freedom. And in independent test of 2 categorical variables, the test statistic follows a chi-square distribution with R minus 1 times C minus 1 degrees of freedom, where R and C are rows and columns number of contingency tables between 2 categorical variables. And the chi-square test statistic calculation has this form, which is the summation of observed value, observed count times the model expected count, take square divided by model expected counts in the table, then take summation for all all the elements in the table. And actually, the chi-square distribution is an example, special example of gamma distribution. So we know this is the gamma distribution density function with the parameter alpha, beta positive real number. But if we let alpha equals nu divided by 2, this alphabet calls nu, which is the degrees of freedom in chi-square distribution. And the beta equals 2, so a gamma random variable becomes a chi-square random variable. So with the following density function. So this is density function for chi-square distribution with degrees of freedom nu. So in this two density function, gamma alphas is an integral of 0 to positive infinity with x alpha minus 1 power times e minus x power conducted integration over x. So the mean of the chi-square distribution is its degrees of freedom, nu, and the variance equals 2 nu. So this is a table called chi-square distribution probability table. So if we look at this alpha is the probability, is 1 minus the cumulative probability associated with this chi-square value in the density function. So this table, from this table we can find from the value for the chi-square value in terms of different degrees of freedom and alpha level. So for example, in a chi-square test, we will find this number if it is larger than the critical value in the chi-square test, or we from these two values from the degrees of freedom and the chi-square value find the alpha level. If alpha or p value less than the critical 0.05, so the test is significant. So chi-square test aims to first calculate the chi-square value and degrees of freedom from observed data, then get the alpha to determine if it is significant, if it is less than 0.05. So chi-square test, also called Pearson's chi-square test, is a statistical hypothesis test for independence between categorical variables. So one of the widely used examples for chi-square test is to test the independence between two categorical variables. And the calculation of the test statistic is based on a contingency table, also called crosstab, which summarizes the relationship between categorical variables. So first we define a null hypothesis. In null hypothesis, we start by defining our null hypothesis, which states that there is no relation between the variables. So there's another hypothesis called alternate hypothesis. It would state that there is a significant relationship between the two variables. So after the calculate chi-square value in chi-square test, we will check if the value of chi-square, so chi-square value calculated if it is less than the critical value of chi-square, which also means if the p-value less than 0.05, so we will reject the null hypothesis and state there is a significant relationship between variables. On the other hand, if the p-value larger than 0.05, we will not reject the null hypothesis and state that there is no relation between the variables. So next we will show how to perform a chi-square test in Poisson. So we have to import function called chi2contingency from scipy.stats module. So if you have not installed the scipy module, you have to install scipy first. So my function is imported. So create a data array. So this array represents a 2 rows, 6 columns table. So next we can run this function of this data. So chi2 contingency data. Then this is the output for the test statistic p-value, the degrees of freedom, and expected several output value. So we also set alpha 0.05. So this 0.05 is most widely used p-value in chi-square test. So next we print out the result. So if p less than alpha, the result is dependent. We reject H0. Null hypothesis will be rejected. And if p not less than alpha, the independent H0 holds true. So you can see in this example, p-value is much less than 0.05, minus 12 decimal point. So result is dependent. These two variables dependent, because this table represents the contingency values between two variables. There are 2 rows, 6 columns, which means the first variable has two categorical values, and the second variable has 6 categorical values, right? So the result is these two variables are dependent, which means reject H0 because p-value is much less than 0.05. Thanks for watching. In this video, we will introduce briefly beta distribution and then show how to use beta distribution functions in Poisson. So the beta distribution is a family of a series of continuous probability distributions defined on interval 0 and 1, and with two positive parameters called alpha and beta. So called alpha is shape and beta is scale parameter. So beta distribution basically shows the probability of probabilities. So because the random variable in beta distribution is only available between 0 and 1. So it is perfect to use beta distribution to model, for example, as a prior distribution in Bayes statistics. Because beta distribution is also conjugate with the binomial, negative binomial, and geometric distributions in Bayes inference. So this figure shows several beta distribution density curves with different alpha and beta. So before we can understand the distribution density function of beta, we have to know something about called beta function. So this is a beta function. So beta function is an integration of the value between 0 and 1. And the integration's form is x alpha minus 1 power times 1 minus x beta minus 1 power. And this formula is also equals gamma alpha times gamma beta divided by gamma alpha plus beta, where gamma is a gamma function. So the gamma alpha is integration from 0 to positive infinity with x alpha minus 1 power times e minus x power. So then we can see beta distribution density function has a form like beta function of alpha beta, then 1 divided by this beta function, and times x alpha minus 1 power, and times 1 minus x beta minus 1 power. So this density formula for the x variable between 0 and 1. So for the other x values, its density is 0. So beta is only available for the random variable between 0 and 1. And note that the uniform distribution we have learned For example, uniform between 0 and 1 is a beta distribution with parameters alpha equals 1, beta equals 1. So the mean and variance of a beta distribution with parameter alpha and beta are mu equals alpha divided by alpha plus beta, and sigma square equals alpha beta divided by alpha plus beta square times alpha plus beta plus 1. And uniform distribution on value between 0 and 1 has mean and variance equals 1 of 2 and 1 of 12. So in Python, if we want to use beta distribution, normally there are 4 functions in module scipy.stats beta. So we have to first import scipy from scipy.stats, import beta module. So beta modules have 4 functions. PDF is probability density. CDF is for cumulative probabilities, and PPF is for quantiles. And PPF is the inverse operation of CDF. And RVS is for the random number generation. So next we will show several examples using these functions in Python. First we import data from scipy.stats and import numpy and import matplotlib.pyplot. So we first show how to use beta density function. We create an array with the value between 0.01 to 1 and with the gap 0.1. So this array called quantile represents the beta variables, because beta variables between 0 and 1. So we use very close to 0 to 1. So next we set A and B representing alpha and beta both equal to 1. So this actually is a uniform distribution. So we can use beta.pdf to calculate the density value associated with this beta variable called quantile with alpha beta parameter. So next we will plot this curve between the quantile, the beta random variable, and its density. So you can see this density function is actually uniform density between 0 and 1, and the area under this curve between 0 and 1 equals 1, because the probability, total probability and density curve will equal 1. So 1 times this length 1 equals 1. Next we will set another alpha and beta value with 2 and 2. Then also run the same function for the density of these random variables with new A and B representing for alpha and beta, and plot the curve between quantile, beta random variable, and their densities. So this is the new curve for beta density with alpha, and for the beta curve with alpha and beta both equal to. You can see the density highest is about 1.5, and the x value between 0 and 1. So the area under the curve is also close to 1. So next we will show a function will generate cumulative probabilities. So first we create quantile same as before, and A and B both equal to. Then we use beta.cdf to calculate the cumulative probabilities of this value with alpha and beta. And similarly, we plot the curve between quantile value, random variable, beta random variables, and their cumulative probability. So the cumulative probability, of course, is an increasing curve from 0 to 1. And next function is called quantile. Usually we call it quantile function, which is to calculate the quantiles, to calculate the beta random variables from given cumulative probabilities. So this is cumulative probabilities. So actually, this operation is inverse of the cumulative probabilities. So cumulative probabilities we have seen is to calculate the cumulative probability from the beta random variable. And here we want to calculate the beta random variable from the given cumulative probabilities. So we create an array called probables, also between 0 and 1, with the gap 0.1. And we set A and B, alpha and beta, both equal to 2, same as before. So next, the function is beta.ppf, which used to calculate the quantiles, or calculate the random variable values, based on the given probabilities. These probabilities is the cumulative probabilities from 0 to 1. And next we print the curve between probabilities and cumulative probabilities in the x-axis, and the calculated quantiles random variables in the y-axis. Show how it is going. So this is also non-negative, non-decreasing curve. So for example, 0.4, which means the probability, cumulative probability, 0.4, the value is about 0.45. So which means for the probability of x less than 0.45, the probability is 0.4. Or we say about 45%, or we say about 40% of the values of random variable in this beta distribution, and the value 0.45, right? So about 40%, because the probability, cumulative probability is 40, 0.4, so we get 40% of values in this beta distribution has a value lower than 0.45. The last function in the beta distribution in Python we will show is generating random variables in a beta distribution. So we set, for example, beta distribution with alpha and beta 6, 2 here. Then we use the function called beta.rvs random value, rvs ab, and size with 10, which means we want to generate 10 such beta random variables. Next we will show these 10 numbers. So you can see all values between 0 and 1. 0 and 1. Thanks for watching. This video we will show how to use Python to work with Lognormal distribution. So first, we take a look at Lognormal distribution. So if a continuous random variable x, if we take the the log form of x, y has a normal distribution with mean mu and standard deviation sigma, then we can say x has a log normal distribution. And the mean and variance of the log normal distributions have this form. So this mu is the log form of x's mu. Then we plus sigma square divided by 2 and take e of power of this part. Then this mu is the log normal's mean. And the log normal's sigma square equals also the e's power part. And in the power part, these two parameters are log of log normal's parameter. Then times e's sigma square minus 1. And these two figures represent the density function of log normal variables with different mu and sigma. So in Python, if you want to use log normal distribution, we have to import scipy.stats module called lognorm. Then we can use 4 functions: lognorm.pdf, .cdf, ppf, and rvs. And they for density, cumulative probabilities, quantiles, and random number generation, respectively. Just keep in mind that in the function a and b, a means the mean of the log normal variable. And b is the sigma. So if we take a look at density function, so in the Python's function, the mean of the location parameter is for this one, not this one. Not this one, it's this mu. It's a log normal variable's mu. And sigma is for this mu, sigma. Because log normal density function has some little different form, but this is the quite normal form. So next we will show examples in Python. We import scipy lognorm and numpy and matplotlib. We will create a quantile array between 0.01 to 10 with the gap 0.5. Because the lognormal variables available value must be larger than 0. So we set a equals, for example, a equals 0. Here, a 0, b is 1. So which means this location parameter refers to log normal variable. So this is what we finally want to be interested in, not the log of the log normal variable here. So this is the mean for the log normal variable. We set 0 and sigma set 1. This is the sigma in the density function. Or sigma is the sigma of the log normal variable. So be careful of this parameter. We set a is 0, b is 1. So next we use the function called lognorm.pdf to generate the density values of this array of variables from 0 to 10 with this location and shape. Sigma also called shape parameter. We plot this density. So you can see the density from 0 to about 0.62 increase very fast. This is change very fast between 0 and about 0.25. Then decrease decrease faster than slowly, close to 0. And the area under this curve, close to 1. So if we set a equals 5, b equals 2 here, you see the location is 5, so location is 5, the mean value is here. So the curve moves. The shape does not change so much. Shape does not change so much for this one. But here, because location is 5, so the value lower than this value equals 0, the density. The next function we will show is CDF, called cumulative probability function. So we set A 0, B equals 1 by default and calculate the cumulative probability associated with this quantile array between 0 and 10. Then we plot the relationship. So cumulative probability is not decrease, and the beginning is increased very fast because the density is quite high, then slower, then almost close to 1. So the highest probability is 1, right? And next function called PPF is to calculate the quantiles from given cumulative probabilities, and this operation is actually the inverse operation of the cumulative probability. So from given cumulative probability, we have to calculate the random variable values. So we set A and B same as before. Next, we create an array called probs to represent probability between 0.01 to 1 with the gap of 0.1. Because probability can be no larger than 1, so we set from 0.01 to 1. Then we can use the function lognorm.ppf to calculate the quantile variables associated with the probabilities array and with the parameter A and B of this lognormal distribution. You can plot the relationship between the probabilities, cumulative probabilities, and the quantile variables. So for example, for the 0.6 represent the cumulative probability 0.6, the value is almost 1.25. So we can say 1.3 about, so we can say almost 60% of the variables in this lognormal distribution less than 1.3, right? The last function we have to introduce is random number generator. So we want to generate lognormal random numbers, 32 such random numbers. So we create n equals 32, A and B. This time we set A is 5, B is 2. We can use lognorm's RVS function. Set the location A, size B, SB, shape as B, size is n. The size is the number we want to generate how many random numbers. You can print these generated numbers. can see very close to 5 because we set the location equals 5, mean value equals 5. With the log of these log normal variables, standard deviation equals 2. So the variation, so the number as large as, for example, 34 has been generated, and most of them around 5, between 5 to 10. So thanks for watching. In this video, we will talk about gamma distribution and show how to calculate gamma distribution in Poisson. The gamma distribution is the probability distribution of the time between events in a Poisson event process. The Poisson event process is a process in which events occur continuously and independently at a constant average rate. So we have learned Poisson distribution at a constant average rate called lambda. And the gamma distribution is used to model the time until alpha times occurrence of such Poisson events. So this alpha, maybe 1, maybe 2, maybe 3, is any number. So the gamma distribution's density function is based on gamma function. And the gamma function is also used in other statistical distribution, such as chi-square, beta. So gamma distribution is a general case of many other distributions, like gamma, beta, and exponential. Exponential distribution is also a particular case of the gamma distribution. So when we want to model the random time until next occurrence of a Poisson event. So if you want to know the random time until next one-time occurrence, so this random variable has exponential distribution. But generally, we can model the random time until next several times occurrence. So this is gamma distribution, right? And in this figure, we show several curves of density functions for gamma distribution. So this one, alpha equals 1, beta equals 1. So gamma distribution has two parameters called alpha and beta. And alpha is a shape parameter, beta called scale parameter. So for alpha equals 1, it is an exponential distribution. So this is the gamma function. So the gamma function is an integration from 0 to the positive infinite value in the real number, and inside this integration's part is x alpha minus 1 power times e minus x power. So if alpha is larger than 0, so the gamma function has some characteristic. For example, gamma n equals n minus 1 times n minus 2 until 1 times gamma 1. So gamma 1 equals 1. Here the equal gamma 1 equals 1. So that which means gamma n equals n minus 1 factorial. And gamma 0.5 equals square root of pi. So from gamma function, we can get the gamma density function, gamma distribution density function. So its formula is 1 divided by beta alpha power times gamma function of alpha, then times x alpha minus 1 power times e minus x divided by beta power. So x larger than 0. So gamma random variable is positive number because we model the time until next alpha times occurrence of Poisson events. So this time have to be positive number. And both alpha and beta are positive numbers also. The mean and the variance of the gamma distribution, alpha beta for the mean and alpha beta square for the variance. So in Python, we can use scipy.stats module and import its submodule called gamma. So next for function called gamma.pdf, CDF, PPF, RVS can be used to calculate the gamma density function. PDF for the probability density, CDF represents cumulative probabilities, and PPF means quantile, and RVS means random variance generation. So here, parameter A means alpha for the shape parameter, and the scale means beta in the formula for the scale parameter, and its default value is 1. So next we will show several simple examples in Python. So first we have to import modules for gamma from scipy.stats and numpy module and matplotlib.pyplot. We create an array called quantile between 0 to 0, 0, 1 to 10 represents the gamma random variable, so with the gap of 0.5. So because gamma random variable have to be positive number, so we set an array between 0 to 10. So we just set A for the shape and scale both equal to 1. Actually A equals 1, which means the exponential distribution. So we create function called gamma.pdf can calculate the density of these random variables with the parameter A equals A, scale equals B. So we can plot the relationship between random variables and associated to density. So this is gamma density function with alpha, beta both equal to 1. Actually, this is an exponential distribution also, because alpha equals 1. So model the density, model the random variable x until next occurrence. So it's a random variable x from 0 to 10, and its density decrease from 1 to almost 0. And area under this curve close to 1. So next function called gamma.cdf is used to calculate the cumulative probability for random variable. So we also set A and B both equal to 1. Then use gamma.cdf with the input this quantile, which represents the random variables. Then A equals A, shape parameter, scale equals B. Then we also plot the relationship between random variables and the cumulative probability. Consider cumulative probability is non-decreasing function of the random variable. The probability from 0 to 1. So the third function is called PPF, which is used to calculate the quantiles, calculate the random variables from given cumulative probabilities. So this function actually is the inverse operation of the CDF, the last one. So we create a probability array called probs with the value between 0.01 to 1 with the gap 0.1. Because probabilities cannot be larger than 1, so we set the value between 0, 0, 1 to 1. So next we can use the function gamma.ppf to calculate the random value x, also called quantiles, from the given probabilities. So we can show the relationship in the curve with the probabilities in the x-axis and calculate random variables on the y-axis. So these random variables also increase with the probabilities. So for example, for the 0.6 probability, the random variable almost equals 1, which means for this gamma distribution, almost 60% of values are less than 1, right? Because here is the probability. And about 80% of values are less than 1.6. And the last function called gamma.rvs is used to generate random variables. So we create n equals 32, a equals 3, b equals 2 here. So we can generate gamma random variables from this gamma distribution with shape equals a, scale equals b, and we want to generate 32, for example, 32 such random number from gamma distribution. We show these numbers. You can see the numbers almost around 5 or 6 because the mean of the gamma distribution equals alpha beta. So mean equals these numbers, two numbers multiplication. So mean equals 6. So you can see the number almost between 1 and 12, right? It's quite understandable because the mean is 6 in this gamma distribution. In this video, we will introduce t-distribution and show how to calculate t-distribution and t-test in Poisson. The t-distribution is related to normal distribution and chi-square distribution. So we look at a variable called t. If this variable is a two parts division and the numerator is a standard normal distribution variable and the denominator is the square root of a chi-square distributed random variable divided by its degrees of freedom, then we can say t is a t-distributed random variable with degrees of freedom nu. And this degrees of freedom number is same as the degrees of freedom of the chi-square distribution in the denominator. And the t-distribution has the density form here is a factor times 1 plus t squared divided by the degrees of freedom, then have a negative power with half of degrees of freedom plus 1. Then the factor is a gamma function's division. So the numerator and denominator both are gamma function. And the t-distributions variable available from negative infinity to positive infinity. T-distribution is quite often usually used in the test of population mean. So if x1, x2, and xn be independent random variables from normal distribution with mu, mean and standard deviation sigma. So if we let x bar equals the sample mean and s square is the sample variance, just note sample variance is the sum of square of the difference between value and x bar sample mean divided by n minus 1. So we divided by n minus 1 here because 1 degrees of freedom is lost when calculating the x bar. So if we have calculated x bar and s square, then the t value, we can call this test statistic from the sample equals x bar minus hypothesis population mean value, then divided by sample standard error divided by the square root of n at the sample size. Then this t-test statistic has a t-distribution with n minus 1 degrees of freedom. So in this figure, there are 3 t-distribution density curve. So this is for t-distribution with degrees of freedom equals 2. And the middle one is degrees of freedom 5, and highest one with very large degrees of freedom. So the highest one is also called normal distribution curve, because if the degrees of freedom in a t-distribution becomes very, very large, so it is very close approximate to a normal distribution. So usually t-distribution's density curve has flat shape than normal curve and has a long tail than normal curve. Now this table is called the t-distribution critical values table. So this, for example, is the t alpha here. So we usually use t alpha as the critical value for test of mean, population mean. So if the calculated sample test statistic larger than this value or less than the negative of this value, the other side, so we can say the test is significant. This is equivalent to that we can get a less p-value than alpha here. So in Python, we use the module scipy.stats import t module. Then from the t module, there are 4 functions called PDF for the probability density, CDF for the cumulative probabilities, and PPF for the quantiles, and RVS for the random number generation. So here, DF parameter means degrees of freedom, and LOC lock is for the location parameter. Here, default is 0. Sorry, default is 0 here. So next we will show how to use t-distribution in Python. So first we import scipy.stats t module and numpy module and matplotlib. So the first function called PDF with a quantile, degrees of freedom and location. So we set a quantile value between -8 to 8 and with the gap 0.1. And we set the degrees of freedom 10 and the location here 2. Then we can use t.pdf to calculate the density value with the corresponding quantile value. Quantile here means t-distribution is a random variable. So this variable means this variable has t-distribution, but we have to calculate the density here. We set a df equals df10, but we use default location here now. Calculated, then we can plot the relationship between quantile random variable and the corresponding density. So this is a quite symmetric t distribution then density curve from the value between minus 8 and 8. You can see the most of the probability stay within minus 4 to the 4, right? Because the density from minus 8 to minus 4 is 0, almost 0. So here, the area between minus 4 and 4 almost 1. So next we can calculate again for this random variable's density if we set the location equals 2 here. So we plot again. So because we set the location is 2, so we know that t-distribution is symmetric. So the location here is also the mean value. So you can see the most of, in this example, most of the value is also symmetrical because we did not shoot to minus 16, right? Because the location is 2. So here minus 4 equals, for example, minus 2's density is same as 6 here, right? So next, the function called CDF is used to calculate the cumulative probability for the corresponding quantile value. We also set the quantile and df and the location same as before. Then we can use the CDF function to calculate the cumulative probability for each of the quantile value. Next, we can plot the relationship. It's quite clear. So because the density between this range almost 0, so the cumulative probability does not increase. Then have start increase, and to this value does not increase because the density becomes 0 again here. And next function is called PPF, is to calculate the quantiles value from a given cumulative probabilities. And PPF is actually the inverse operation of the CDF, right? The PPF calculates the quantile values from the given cumulative probabilities. So we set df and location same as before. We also create probabilities array between 0.01 to 1 because probability cannot be larger than 1 and with the gap 0.01. So we can calculate quantile value or the random number value from t-distribution if we know the cumulative probabilities. And next, we show the relationship between the probabilities, cumulative probabilities, and the quantile value. This curve is the inverse curve from the PPF, from the CDF, cumulative probability. So, for example, 0.6 here almost we can see 0.5, for example, here is about 2, because this t-distribution has a mean value. We set the location 2 here, so which means 50% of the value in this distribution has 50% of the random variables has value lower than 2, right? So the last function is called RVS to generate random numbers from t-distribution. So we can create, for example, 10,000 random numbers from t-distribution with 10 degrees of freedom. So we use t.rvs, 10, size is 10,000. Then we can plot this created value in histogram with bins 50. So this curve is very similar as the density curve, but this is a histogram. The shape is quite same. It's almost symmetrical, but not exactly symmetrical, because this is a random number generated, so it's not perfect symmetric. For example, here, not exactly the same symmetric, right? Because we set the location default value, so you can see the highest frequency value is 0. Mean value, also median value, also the mode in this distribution is 0. So next we can set the location to 5, then create also 10,000 values. So plot again histogram. So this time the mean value or the mode is very close to 5 now, right? So now we will show an example of using t-distribution to do t-test. For t-test for the population mean. So the example is a chemical engineer claims that the population mean yield of a certain batch process is 500 grams per milliliter of raw material. So to check this claim, he samples 25 batches each month. So if the computed t-value falls between minus t0.05 and t0.05, he is satisfied with this claim. What conclusion should be drawn from a sample that has a mean x bar equals 518 grams per milliliter and a sample standard deviation s equals 40 grams? Assume that the distribution of yields to be approximately normal. So this is a typical t-test problem, right? Because the population is normal and we use the sample mean and a sample standard error to do the test. So the test statistic calculated in this form will have a t-distribution, right? So we import module called mass, because we use for the square root. So first of all, we have to calculate the critical value of the t-distribution with 24 degrees of freedom and 0.05 here. So we want to calculate the critical value t alpha here, because in this test use 0.05, or alpha is 0.05. So we have to calculate the t alpha. Do not use the table, just use our program. So the t critical value equals the t dot ppf. ppf means quantile. We want to calculate the quantile from the given probability. So the given probability is 1 minus 0.05. Because the ppf is calculated the cumulative probability through the t alpha. So this is white area. The white area under the curve is 1 minus alpha, right? So we use t dot ppf 1 minus 0.05, then use 24 degrees of freedom because there are 25 observations in sample. So it is about 1.71 for this t value, for the critical value in this curve, right? So next we calculate the t sample. So sample statistic, test statistic. So t sample statistic is from this form, right? We have mu, assume the mu, and we have standard error from the sample. We have the x bar for the mean, for the sample mean value, right? And n for the sample size. So everything is ready to calculate the t sample. Just fill in the form. Then t sample is 2.25. So we can do another step from this t sample. So this is sample test statistic. We can also get the p value. So t sample is here. This is the t critical value for the test critical value. T sample, because 2.25 is almost here. So we can calculate the probability, shaded probability associated with this test statistic here, right? So we can use the CDF function now. T.CDF, T sample, then use 1 minus calculate the probability, we get this p value. So it's about 0.0169. So the conclusion can be drawn because t sample test statistic from the sample larger than t critical value because 2.25 larger than 1.71. Also means p value calculate less than 0.05. So 0.05 is the significance level we assumed before we test, right? So the engineer is likely to conclude that the process produces a better product than he thought. So which means these samples comes from a population with a larger than 500, not 500. So because if we assume the population mean is 500 is correct, then there's only about 0.01 probability can get such sample. So this is quite a low probability. So we can safely reject the hypothesis that the population has a mean of 500, right? So I'll say in this test, the test result is significant. It's significant because the test statistic larger than the critical value, and also the p-value, this is same as the p-value calculated from the sample is less than the p-value, the significance level 0.05. So the hypothesis of population mean is 500 is rejected. Thanks for watching. In this video, we will talk about quantile plot and show how to plot a normal quantile plot in Python. So first, we will show what is a quantile. So quantile of a sample, or called QF, actually is a value for which a specified fraction f of the data values is less than or equal to QF. So quantile Q actually is a random number. It's the value of the random number from the observation. And it is related to a fraction called F, or called the cumulative probability. So the fraction of the observation in this data set is less than this quantile number. So we call this is a quantile of F. So if we let the order of the observations, so from 1, 2, 3, 4, for example, to the 20, ranked from the low to the high value of the number associated with 1, 2, 3, 4, 20, right? And the fraction can be calculated as I minus 3 of 8 divided by n plus 1 of 4. So this Fi number for each observation is between 0 and 1. And this number is also increasing